So today we will start with eigenvalue and eigenvector. For the last video, we have done the matrix. Today we will do the eigenvalue and eigenvectors. So before going to the definition of eigenvalue and eigenvector, we will start with the basic idea why this eigenvalue concept of eigenvalue and eigenvector comes. Now, let us consider a matrix A, any matrix, any 2 cross 2 matrix, along with two vectors u and v. So after taking u and v, just first we will compute au and av. So if you see, au is actually -5, -1, and av is 4, 2. So 4, 2 we can write it as 2 into 2, 1. So basically it's 2 into the matrix v. So if I interpret it geometrically, if this is the vector v, if this is v, then then AV is representing in this direction, that is AV and V are having in the same direction, whereas U and AU are in completely different direction. So in our case, we are only interested in this kind of vectors v, where the multiplication with the matrix A with this vector will give the output in the same direction. We are not interested in different direction matrices. We're only interested in those kind of vector where AV and V are in the same direction or they are parallel. So here it comes the eigenvalue definition, official definition of eigenvalue and eigenvector. So definition starts with, if A be a square matrix, real or complex, it can be real or complex, the entries can be complex also, then a scalar lambda is called the eigenvalue of A if there exists a non-zero vector x such that Ax equals to lambda x. That means if you multiply A with a vector x, there will be a scalar multiply. Like in the previous case, it was 2, like same constant multiplied with the same vector. If that comes, then that scalar lambda is called the eigenvalue and the corresponding x will be called the eigenvector. So this is the eigenvector and this is lambda is the eigenvalue. Now there are 2 points we have to take care. One is non-zero vector. We are only interested in non-zero x, because if it's a zero vector, then obviously it will satisfy. We are not interested in trivial solution. We're interested in non-trivial solution, that is x must be non-zero vector. Another is this is called eigenvalue and this is called eigenvector. So that's it. Now there are two kind of definition that comes from eigenvalue and eigenvector. One is, there are, if then in this equation Ax equals to lambda x, how many unknowns are there? Unknowns are, because A, the only thing given is A. So the unknowns are x and lambda. So we have to find out both eigenvalue as well as the eigenvector. Lambda and x we have to compute. So one by one we will compute. First we will compute lambda. So how to compute this we will see, but before that, this definition of eigenvalue or eigenvector, there are different kind of interpretation. Like geometrically, if you want to interpret, you have to tell in this way, like we are searching for this kind of vector x for a matrix A such that x and Ax are parallel, they will be in the same direction. We are searching those kind of vector x such that it's a scalar multiple of other. And if I want to interpret it algebraically, then I can tell in this way, that if Ax equals to lambda x, I can write it in this way, Ax minus lambda x equals to 0. So A minus lambda I into x equals to 0. So that this is basically a homogeneous system of equation and we are searching for a non-trivial solution. X should be non-trivial, x is the solution, which is the eigenvector. So the eigenvector is basically the non-trivial solution of the homogeneous system of equation A minus lambda equals to 0, or in another way we can write it as x is a solution of the null space A minus lambda I equals to 0. So that what I have told, that geometrically and this is algebraically. So there are multiple theorems on eigenvalue and eigenvector which shows various properties. Everything, for everything there is a proof, but due to lack of time, I can't go for the proofs. But two important properties we have to keep in mind when we go detail for eigenvalue and eigenvector. One is, if there are multiple eigenvector for the same matrix A, they will be linearly independent. There shouldn't be any dependency. One cannot be the scalar multiple of other. No, if they're they will be linearly independent. If there are n number of vectors, n will be linearly independent. We are searching for the linearly independent eigenvector. Another is, if suppose x is an eigenvector, then any scalar multiple of x is also an eigenvector. But the thing is that x and ax are not linearly independent. X and lambda x is linearly dependent. So there are infinite number of linearly dependent eigenvector, but x is the generator, or x is the basis of this set. So that's it. Now, how to find out this eigenvalues and eigenvector? So for finding out eigenvalues and eigenvector, uh, we have to consider the equation A minus lambda I into x equals to 0, which we have already shown that this is the basic equation of eigenvalues. Now, if A minus lambda x equals to 0, this is a homogeneous system of equation, and I want a non-trivial solution. Then for a homogeneous system of equation, we'll have a non-trivial solution only if the determinant A minus lambda I equals to 0. If determinant is non-zero, then there will be the unique solution, which is 0, and we are not interested in 0 solution. So determinant of A minus lambda equals to 0 is the only condition to have a non-trivial solution. Now if determinant of A minus lambda I equals to 0, if we expand it, A minus lambda, how it will look. If A is a n cross n matrix, then A minus lambda means diagonally we are shifting lambda. So there are numbers, and if you expand it, it will be a nth order. If n A is a n cross n matrix, there will be a nth order equation of lambda, which C0 is either one plus or minus 1. And this, from this equation we can have n root, lambda 1, lambda 2, dot or lambda n root. N root means there are n eigenvalues. There can have less than n number of roots. There can have multiple roots also. But from a nth order equation, I can have n root. There can be multiplicities, but n root will give n eigenvalues, and this equation is known as the characteristic equation. Roots of the characteristic equation, as I told, is called the eigenvalues. Now we see an example. So there are several properties. Properties, we can go for the properties. Okay, like this one. Okay. So there are several properties, like every property has a proof, but again, I'm not going for the proofs. So some of the eigenvalues will give the trace A, product of the eigenvalues will give determinant A. If a matrix is a singular matrix, a 0 will obviously be the eigenvalue. Similarly, any scalar multiple will have eigenvalue with the same eigenvector. Similarly, power will have the power of lambda, but with the same eigenvalues. A inverse will be lambda inverse. A transpose will have the same eigenvalues. Eigenvalues will lie on complex conjugate number. So these are some of the properties which we will use again. So we can go for an example. Example for finding out the eigenvalue and eigenvector. Suppose A is a matrix, so we have taken a simplest example for a 2 cross 2 matrix. Now to finding out the eigenvalue, I have told the basic thing is A minus lambda is equals to 0 determinant. So if we do A minus lambda, it's 1, 3 minus 1, determinant equals to 0. So if we expand it, we'll get this equation where 6 is the trace, sum of the eigenvalue, sum of the root trace. 8 is determinant, it's the product of eigenvalues, product of the roots. So from which we have two roots implying two eigenvalues, 2 and 4. So corresponding to each eigenvalue, we can have an eigenvector. So this will be x1. So for this, we have A minus 2y into x equals to 0. We have to search for x. This is again a system of equation. In linear algebra, from the beginning, we are only emphasizing on the system of linear equation. So here again a system of linear equation for the eigenvalue 2, and we can find out x is minus 1 1. Similarly for the 4, for the value 4, I have a minus 4 I equals to 0, which will give x equals to minus 1 1. So there are two eigenvalues corresponding to two eigenvectors. So yeah, that's it. Acha. Next, we will go for a theorem, which is a pillar. We can tell a pillar of eigenvalue eigenvector, which is Cayley-Hamilton theorem, which is telling us that every square matrix satisfies its own characteristic equation. What is the meaning? The meaning is that if a square matrix is given, I can have the characteristic polynomial easily in terms of lambda by determinant of a minus lambda equal to 0. I have shown there will be a nth order polynomial, sorry, nth order equation of lambda. So this Cayley-Hamilton theorem is telling that if we replace lambda by a, then it will be again satisfied. So right hand side will be a matrix now. It's a n cross n matrix. It's CNIN. So it's a very useful theorem to find out inverse if I don't want to compute conjugate of a and all. Also algebraically, by just simple algebraical calculation, I can easily find out inverse of any matrix, or by if you want to compute power of any matrix like a to the power 50, a to the power 100, that this theorem also very useful for by reduction formula. We can reach there. So as I told, suppose A is this, then A inverse will be this. I can tell it by Cayley-Hamilton theorem. So a to the power 50 also we can compute. A to the power 50 will be this one. So this is one of the examples. Okay. Now, there are some characteristics of eigenvalues if the matrix has some special matrices. Like there is a proof which is telling us that if A is a real symmetric matrix means A transpose equals to A. If A is a symmetric matrix, then the eigenvalues are always real, and it happens for a Hermitian matrix also. For a Hermitian matrix also, the eigenvalues are always real and the eigenvectors are orthogonal. So that's why uh, this is called spectral theorem, which is telling that the eigenvalues are always symmetric and eigenvectors are eigenvalues are always, sorry, eigenvalues are real and eigenvectors are always orthogonal. Similarly, for a real skew symmetric matrix, it can be concluded that the skew symmetric means A to the A transpose equals to minus A. For a real skew symmetric matrix, eigenvalues are either zero or purely imaginary. There will be no real number that can be eigenvalue or eigenvalue of a skew symmetric matrix. Similarly, for skew Hermitian matrix also the same case, either zero or purely imaginary. For an orthogonal matrix where A transpose equals to A inverse, for an orthogonal matrix, all eigenvalues will have unit modulus. That means lambda I will be 1. If it's a real number, then it's always plus minus 1. If it's a complex number, then it will be in such a way a plus ib such that root over of a square plus b square will always give 1. So if I put it in a geometrical way for a two-dimensional coordinate system, all the eigenvalues for real symmetric matrix will lie on the real number line, whereas all the eigenvalues of the skew symmetric matrix will lie on the imaginary number, including 0, and all the eigenvalues of an unitary matrix will lie on unitary or orthogonal matrix will lie on modulus of lambda equals to 1. That is the unit circle. So now we will go for some applications of eigenvalue and eigenvector. And in application, first thing comes is diagonalization. Diagonalization of a matrix, how I can diagonalize a matrix, how I can make a matrix similar to a diagonal matrix so that I can compute so that it takes lesser number of computation to finding out inverse, to finding out any power of that matrix, or uh, anything easier to find out if it's similar to a diagonal matrix. So before going to the diagonalization, we have to know what is a similar matrix called. Uh, Suppose there are two matrices A and B. See that we can see the definition. So suppose there are two matrices A and B, then we can tell two matrices A and B to be the similar matrix if there is a non-singular matrix P. This P matrix we have to find out. There are some mechanism by which I can find out the matrix P such that P inverse AP is equals to B. If that happens, that P inverse AP is giving B, then B and A are called similar matrix. Why they are similar? Because there are many similar properties, like they will have the same determinant, they will have the same trace. Similarly, um, they will have the same characteristic polynomial, and similar since they have the same characteristic polynomial, obviously they will have the same eigenvalue, but the eigenvectors are not definitely same. Eigenvectors are different, but the eigenvalues are same, because if the characteristic polynomial are same, then the roots are same, so the eigenvalues are also same. So, and many other characteristics are there. So that's why these two matrices are called similar matrix. And this P is called the model matrix. So, as I have told, they will have the same characteristic polynomial, and they will have the same eigenvalue, but the eigenvalues are different. Like if A is X is eigenvector of A, then P inverse X will be the eigenvector of B. Okay, now we come to the original thing, which is diagonalization. Now, a matrix A, suppose a matrix A is given. So every matrix will not be diagonalizable. There are some conditions, some restriction on A. And based on the restriction, we can tell this is diagonalizable and this is not. So what is the condition? A matrix A will be called diagonalizable if there exists an invertible matrix P. So P is a very special matrix, and there is a special technique to construct P. I'm coming. Uh, Invertible matrix P such that invertible because I'm using P inverse, so definitely P inverse should exist. So P inverse AP is a diagonal matrix. That means this definition is actually telling that you have to find out a P for which P inverse AP will be equals to D, the diagonal matrix. We denote the diagonal matrix by D. That means we are making A and D similar. That is the given matrix and a diagonal matrix we are making similar. And if they are similar, I can tell A is diagonalizable. So this is the definition. And what are the restriction by which I can tell this is diagonalizable and this is not? The restriction is A is said to be diagonalizable if and only if A has n linearly independent eigenvector. Like for a matrix A, which is a n cross n matrix, I need n eigenvectors which are linearly independent. If it's n minus 1, it's not possible. If it's n plus 1, so it's not possible at all. But if it's n minus lesser than n, then we can conclude no, it's not diagonalizable. So otherwise it's diagonalizable. And how in linearly independent eigenvector it can be? If there are n eigenvalues, in distinct eigenvalues, then eigenvalues or eigenvector will be linearly independent. But it's not sufficient, because if there are n minus 1, there can be multiple, but in eigenvectors can be there. But this is one of the necessary condition to be diagonalizable. Okay, now as I told, this is called the model matrix. Okay, and how to construct P? I have told that there is a special way by which I can construct P. So P is basically this matrix. If A is an matrix with eigenvalues lambda 1, lambda n, and eigenvectors x1, xn, then P will be first column x1, second column x2, third column, last column xn. Just column wise, you are putting all the eigenvectors, n eigenvectors, and this will give the matrix P. And if you construct P in this way, then obviously P inverse will exist, and then you can find out P inverse AP. And after multiplication, you can find out this D. There is a proof, but I can't show it because of lack of time. But D will none other than this matrix, lambda 1. It's a diagonal matrix. Only the diagonal elements will be these eigenvalues according to this order. lambda 1, lambda 2, dot, 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 lambda n. This is D. So if you construct this P, you can check that P inverse AP will always give this diagonal matrix. Now we can see an example like if this is A with eigenvalues 1 and 6 and eigenvectors this, then P will be first column, second column. This is P. So P inverse is D. And if you compute P inverse A P, it will give the diagonal matrix. What are the diagonals? 1, 6, 0, 0. So this is the matrix. This is D. So this is how we can come to the conclusion. Acha. So example of using this diagonalization is since P inverse AP is D, similarly I can multiply it by P inverse left by P right by P inverse. I can have A equals to P D P inverse. So I can have any power of A. Like suppose I'm trying to find out A square. So A square equals to P D P inverse. P D P inverse. So this will give identity. So it's actually P D to the D square P inverse. Now, if D is a diagonal matrix, like suppose simplest example lambda 1, lambda 2, 0, 0, then D square will be nothing but lambda 1 square, 0, 0, lambda 2 square. Since diagonal, so diagonal elements will be squared. So any power of A I can easily find out by this diagonalization. So this is one example. Another very important example is to solve a system of differential equation. So there is a technique. If A is diagonalizable, if I can give the assurance that A is diagonalizable, then I can easily find out the eigenvalues and eigenvectors and I can construct P. So P is after construction of P, we have x dot equals to just we are replacing A by P inverse, sorry, P D P inverse. So I'm replacing this is A, and after replacing A, just multiply both side by P inverse. So this is d dt of P inverse x, right? ddt of P inverse x equals to dP inverse. So I'm replacing P inverse x by y. So this is equation y dot t equals to dyt, where D is a diagonal matrix with the eigenvalues. So y1 dot y2 dot is a column vector equals to diagonal lambda 1, lambda 2, lambda n. That means this is this matrix lambda 1, lambda 2, lambda n, and rest everything is 0 into this. So y dot t equals to lambda 1 yt. Similarly for n elements. So I can integrate easily by integrating taking this and this. So solution will be for each I y it equals to c1 e to the power lambda it, right? So this is for any I, and c is a scalar. Now I have P inverse x equals to y. So easily I can find out x as x equals to P into yt. So P is this matrix. P is x1, like here I have written v1, v1, v2, vn into this. So this will give all the x1, x2, dot, dot, xn, the solution of the system of differential equation. So this is another example. We can use it to find out the population problem like decay or growth rate, and also we can use there. So these are some of the examples, and these are some of the books I have taken reference from. Thank you.